Hello, I am Ingrid Moerman from IMEC, where I am a member of the ID Lab research group embedded at Ghent University. I am happy to present our vision on 6G called Mandate-Driven Networking Ecosystem, a paradigm shift in end-to-end communications. This vision is the result of several brainstorm sessions between researchers from different research organizations as listed at the bottom of this slide. Let me just start with a disclaimer. First of all, I want to clarify that our vision is not violating current 5G or 6G evolutions, but it broadens the scope. Next, in contrast to most 6G visions, our vision is not driven by technology, but it is technology neutral, implying that our vision is backward compatible with existing technologies and future-proof for new technologies. Our vision is mainly driven by end-to-end mandates, and those mandates are steered by the needs of professional markets. What are mandates? Well, it is derived from to mandate, meaning to order someone to do something. In networking terms, someone refers to the network, and to do something means to support network services, services that have to comply with dynamic end-to-end quality of service needs from applications, and services that have to respect profiles and preferences of users and machines. I will continue with some observations. Networks today behave as isolated systems, focusing on optimizing their own operation. Unfortunately, networks are not omnipresent, and it is hence hard to believe that a single technology or a single operator can manage all end-to-end communication needs. And further, smaller, local, dynamic environments may require more flexible, lower cost, more embedded solutions than 5G without the need to delegate operation to an external network operator. In addition, current network designs are network-centric and do not consider applications and end devices as a full part of the network. For this reason, it is hard for applications to communicate their demands to the underlying networks with sufficient variety and granularity. Applications also have to be aware of the supporting networks, as each network has its own specific SLA agreements and quality of service classes. Today, networks cannot monitor the requirements and performance of applications in real time. A lot of data is measured, but mostly limited to link and radio level, not truly end-to-end. It is hard for an application to verify what is the actual service it got from the network, because the measurement data needed to perform end-to-end network management for maintaining the required quality of service level is missing. Another observation is that the way data is accessed is mostly dictated by operating systems, single vendors or providers, rather than by the users. Let's now zoom in into the vision and start with the application view. It all starts with the application, or with the user who interacts with the application via a human-machine interface. An application further communicates with other applications involving another user or a group of users. To reduce or eliminate the need for human interaction, our vision proposes three generic profiles. A first one is the generic user profile that contains personal data and preferences related to data protection, application preferences, and priorities. For examples, priorities can have an influence on which applications are still allowed in case of battery depletion, ensuring that battery resources are guaranteed to support VoIP calls at any time. The generic user profile can be largely created automatically and is independent from type of device, operating systems, applications, and networks. A second profile is the generic device profile, containing information on ownership and access control for users. A third profile is the generic network profile, with information on network security and protection policies and compliance with regulations. Of course, contexts such as location, time, weather conditions, presence of other persons in the environment, battery status, activity, mood, etc., will also influence the needs of the application. And such context information, when discovered, can be dynamically added in the generic profiles. An important enabler in our vision is the way an application expresses its end-to-end needs and intentions. Our vision promotes an expressive API that is technology and operating system agnostic, leading to absolute freedom for implementation and distributed optimization. There exist different interaction models. In addition to human interaction, we also can have interaction between a human and a device or a server, or between devices, also called machine-to-machine interaction. Another view in our vision is the infrastructure view, as the interaction between applications needs to be supported by end devices and communication infrastructure in between. For example, an application on a smartphone can interact with a server in the cloud. We can have different types of communicating devices, from tiny sensor devices and smartphones to high-end servers and storage devices in data centers. Between the end devices, we have a physical network infrastructure that offers a broad range of wired and wireless connection technologies. While 5G brings a lot of innovation in the infrastructure, we believe we should not ignore the capabilities of end devices, and therefore our vision recommends to bring in the terminal in the design process by introducing more open and more reprogrammable air interfaces that can facilitate, personalize, context-aware and graceful degradation of the terminal, based on the generic profiles discussed earlier. This will allow to introduce distributed intelligent services from the cloud to the edge in network elements as well as in end devices, and take advantage of adaptive AI and machine learning approaches for real-time analytics, decision-making and resource optimization. The last view of our vision is the connectivity view. This view explains how to establish, control and manage end-to-end communication services between humans, applications, devices and machines for optimal communication support. The connectivity view is again driven from demands between applications. End-to-end communication is realized by combining multiple wired, optical and wireless network segments and administrative domains. Each segment is independently managed by a separate domain-specific orchestrator, offering maximum granularity of configuration option in each segment. Selection of network segments and administrative domains is based on context-aware understanding of the application and/or user environment, where context is derived from dynamically updated generic profiles. Selections of segments and domains is also based on purpose-aware understanding of the network environment, where the purpose is derived from segment-specific capabilities and constraints. Examples of segment capabilities are mobile wide area coverage or time-sensitive support. An example of a constraint is the current load in a segment. For the coordination of end-to-end resource allocation across segments, our vision proposes an intelligent cooperation plane with distributed agents in each segment. The distributed agents exchange information that allows selection and proper configuration of the segment. An important innovation in our vision is to extend the notion of management control and data plane separation to the application level. For instance, by bringing the application in the design process, applications now can make mandates known to the networking stack and the entire end-to-end path, which will trigger a negotiation process in the intelligent cooperation plane for selecting and configuring segments. More attention needs to be given to real-time monitoring, not only in the network segments, but also at the application level. Measurability can even become an inherent part of every data transfer. For example, in-band telemetry mechanisms can inject crucial measurement data such as information on timing or queue occupation into data packets at different monitoring points. This will facilitate end-to-end runtime verification of the actually achieved quality of service, and this will trigger feedback to the segments to proactively fine-tune configurations in order to maintain the desired quality of service level. Distributed intelligence in end devices as well as in network infrastructure components will support the monitoring, negotiation, decision and configuration processes. A very promising approach is decentralized and federated learning, where on-device learning based on local data is combined with central computation. Such an approach can drastically limit information exchanges and increase spectral, bandwidth and energy efficiency, and also improve privacy protection. Again, we have different interaction models. Firstly, communication between end devices over network infrastructure. Secondly, communication between end devices and servers also over network infrastructure. And finally, direct device-to-device communication without network infrastructure. Now we have the full view on the mandate-driven end-to-end vision. The main innovation in the application view is that application can express their mandates assisted by dynamic generic profiles. In the connectivity view, we have dynamic decomposition in segments managed in a distributed way, hereby assisted by the intelligent cooperation plane and supported by many measuring points, also in end devices at the application level. For the infrastructure view, our vision foresees a more prominent role of end devices in intelligent end-to-end configuration and management. In summary, our vision promotes to involve end users, terminals and applications in the overall design of end-to-end communication. We are confident that our vision broadens research and innovation. In the first place, from a telecom-centric view to an end-to-end mandate-driven and purpose-driven view. Our vision further extends research and innovation from a limited number of actors dominated by big mobile stakeholders to multiple actors, also involving smaller players and academia. We also see a shift from large public to many and smaller private networks. The paradigm shift we propose is technology and actor neutral and can be implemented independently of any specific technology generation and business relationships. We finally believe that our vision will lead to simplified standardization and specification processes based on technology and operating system agnostic expressive interfaces. We hope you like our vision. If you want more information, please have a look at our paper. If you have questions, don't hesitate to contact me. Thank you.